to the presenter?
Okay, we are recording now.
Okay.
Go ahead.
So, Marcio, go ahead.
So thank you, Sid, and thanks, Professor Grelu, for accepting our invitation. It's a great pleasure and honor for us to have you here. So I'll be quick. Professor Philippe Grelu graduated from University of Bourgogne he graduated from École Centrale de Paris in 1989. He got his PhD from University of Orsay in 1996, and he was, I suppose he was hired in University of Bourgogne in 1996. So it's a very fast track. And the main research areas, fields that he worked is nonlinear optical cavities cavity dynamics, dissipative solitons, extreme Rogue waves, between and other stuff. So how did we never met before in person. So I started to work with nonlinear dynamics for femtosecond fiber lasers, and then I saw that most of the relevant work done in the field has his name on it. So lots of very nice publications on this area, and his name came up to this to our colloquium. So thank you very much for coming here again, and it's our pleasure. So that's it.
Thank you very much, Professor Nacho Miranda, for this kind introduction. Yeah, so I should share my my screen. I don't know if you...
Yeah, it's okay.
It's okay. Okay. Sorry. So I should move on with the...
Yeah.
All right. So now full screen. Do you have the full screen of the first slide? All right.
Yeah, it's okay.
Okay. So, right. So the purpose is, of course, to have a mix of different topics with a gradual complexity, so that at least in the beginning, I hope that the whole audience should clearly see what I'm presenting and gain some insight. So a bit about my place. So I'm in Dijon. Dijon is around 300 kilometers from Paris, and so we're within a federal university, which is UBFC, Université Bourgogne-Franche-Comté, so there are several campuses, and I'm in the Dijon campus, so it's on this map roughly like 1 kilometer by 2, and on this campus there's around 30,000 students and 3,000 staff people. So it's a general university, which means that you have laws, humanities, medicine, and physics and chemistry, engineering. So my lab is the ICB, which is affiliated with CNRS, and we are around 300 people in physics and chemistry, with 6 departments. So I'm actually the head of the photonics department, and we also have one international master degree program on physics, photonics, and nanotechnology. So just a few keywords. Of course, I don't have time to develop this expertise from the people from my department. Just a few keywords so that you can see the areas. So basically, the center of mass of activity is fundamental and experimental, but in general, it will also span from theory, modeling experiment, and also technology and applications. There is one big line of activity about nonlinear propagation in fiber optics, gas, plasma, which means different kinds of materials, with also an emphasis on ultrafast dynamics. There's also a line on nonlinear dynamics in optical fibers, optical systems, lasers, for the development also of coherent sources. And also a line with plasmonics, nanophotonics, sensor applications, also with a small facility for like clean room facility for fabrication, especially in plasmonics. All right, so that's my little team of collaborator within the photonics department. So we are 4 professors and associate professors. We have like 2 PhD students who are actually on their final year. One optical engineer, 2 postdocs who came this year, and also 2 previous postdocs, which we remain in contact because they're, we still interact with them. Okay, it's time to give the outline of my talk. So first is to expose the notion of solitons. So I will go through the physical effects which are involved, the nonlinear Schrödinger equation, and also we'll give some analogies which are very interesting to get more insight. Second part will be devoted to going into ultra-fast fiber laser area. So I will give some elements of technology, and then the major concept of dissipative solitons with the nonlinear tools of attractors and bifurcations, and I'll leave some time also for what I call the weird research zone with some strange phenomena which can be observed. All right, so this soliton is a very interesting concept. It was also thought for applications in optical communications, but to be honest, not so much these days because there are other technologies there. But still, a soliton remains a very important concept for the development of other applications. For instance, with solitons, you can think of using the help from Raman effect to have frequency conversion. This is the case with soliton self-frequency shift in single mode fibers, but it's also possible to have like big shift in multi-mode fibers. There's also the role of the solitons in many cases of supercontinuum generation. So the idea here is to also to broaden the spectrum, to have new frequencies for any kind of applications. For instance, if you want to do some kind of spectroscopy, yeah, so that's been, and it is still a very important subject. And also solitons are involved in mod-lock fiber lasers, but I will explain this later. And in my talk, I will just develop these 2 aspects, soliton propagation and mod-lock fiber lasers, just to say that ultrafast nonlinear optics has a lot of different subtopics. So let's speak about nonlinearity in optical fibers. So in optical fibers, most of optical fibers are made of glass materials, and glass materials are centrosymmetric materials, which means that because of symmetry, the second order nonlinearity and all even orders should vanish. So the first nonlinearity to come is the third order nonlinearity. So because it's a kind of Taylor series expansion, one may wonder whether this nonlinearity would be observable, would be large enough to have significant effects. So actually, you can play with the physical parameters to have a large nonlinear effect. So what you need is to enhance the optical intensity and to have an increased propagation length. And this way, you can have access to significant third order nonlinearity. So for optical intensity, well, the recipe is that you can increase the peak power if you work with short or even ultra short pulses. And also you can reduce the effective mode area, especially if you focus the pulse, and more to it. If you focus and then you propagate within a waveguide, then you will also have the benefit of the long propagation distance. So that's the way to really access this third order nonlinearity. There are different third order nonlinear processes. Of course, in general, you need phase matching. This might be difficult, for instance, if you want to have like a third harmonic generation, but there is one third order process, which is self-phase match, which means that it will occur at whatever the optical wavelength, and this is the optical Kerr effect. So the optical Kerr effect results in a modification of the optical index. This way, we have the optical index, which has this additional term where there is N2, which is the nonlinear refractive index. So even though it's rather small, for instance, for silica, it's around 2.7, 10 to the minus 7 watt minus 1 square meter. But with using a focused beam and coupled into an optical fiber, you can enhance this optical Kerr effect. Another possibility, if you work with lasers which are not coupled to an optical fiber, is to have high intensity. So actually, in 2 or 3D propagation, there is this effect of self-focusing, which means that the pulse profile will make also a nonlinear phase profile, and that is able to focus the pulse itself. So it's self-focusing, and this can be used as a technique for mode locking of bulk laser. This is called Kerr lens mode locking. At even higher powers, or even higher with higher nonlinear material, you can also have a beam collapse, and to start starting the generation of a filament. Okay, but now we will go into the area of fiber optics, where the involved optical field intensity are not so high, and we can wonder, so what kind of effects should we observe? So to be convenient, we define the effective nonlinear coefficient gamma, which is basically the N2 divided by the effective mode area times K naught. And we come with the major effect, which is sulfate modulation. So if we take sulfate modulation alone, it will not change the temporal intensity profile. It will not change that. However, it will imprint a phase shift, which depends on the optical intensity, so that it will imprint on the pulse a nonlinear phase shift, which will have the same shape as the intensity profile. So now the consequence is that since we have this added nonlinear phase, which depends on time, then we can define the local detuning, which is the minus the derivative of this nonlinear phase with respect to time. And just by simply derivating this profile here, we see that it will lead to redshifting in the leading edge of the pulse and blue shifting of the frequencies in the trailing pulse edge. So new frequency will appear, a bit like in this kind of rainbow pulse, just to give an image. Even though if we just have sulfate modulation, the pulse, for instance, the pulse duration, the pulse shape will not change, but the spectrum will evolve along with propagation. So if we follow this spectrum along with propagation, we will have this evolution with a broadening because new frequencies appear, but also this weird oscillation in the spectral domain. And the reason can be explained here is just because, for instance, you can have two places on the pulse in the time domain where you have the same slope, like here and there, the blue dots, and thus when derivated, it will give the same frequency detuning, so the same frequency, same new frequency components. However, they have an offset delta phi of a phase offset, which means that they will interfere either constructively or destructively, and that's the reason why you have this developing oscillatory structure in the spectrum for sulfate modulation. Now let's have a look at another important effect, which is a linear effect, which takes place in the optical fiber because of the accumulated distance. It's the chromatic dispersion. So there are two regimes of dispersion. The normal dispersion regime, where if we take two wave packets, so basically the red will travel faster than the blue. And that's just an image. Red means a longer wavelength. So the red travels faster. And there's another regime in silica is for the wavelength larger than 1.3 micron. It's the blue wave packet that will travel faster. So the result of that is that any pulse feeding that chromatic dispersion will have an evolution. If we're in this linear propagation regime with only chromatic dispersion, you will have this pulse broadening. So with a pulse chirp, which will appear with this different frequency, which will be just dispersed along the pulse, depending on the dispersion sign, represented by these two colored pulses here. So, of course, we have a complete math about this problem. And probably you know a bit of the math. So, I don't know, maybe most of the students, master students, for instance, will study Gaussian beams. And in fact, we have a complete space-time analogy with the propagation of Gaussian beams. So Gaussian beams, they feel diffraction. So that's the reason why they expand. But you can take a Gaussian beam with some phase curvature so that the beam will first be focused and then will expand, will be defocused. And we have the same in the time domain, the equivalent in the time domain with pulses. So pulses, they can have, because they can also have an initial chirp, and according to the chirp and the sign of the chirp and the sign of dispersion, so either they have this broadening, or they can self-compress in the time domain and then broaden. Completely equivalent between the propagation of Gaussian beams. So now we understand that we have two dispersive effects, which will be generally quite important for pulses in optical fibers. And we have on one side Kerr nonlinearity, with sulfate modulation that will make some blue shift in the leading part of the pulse. And we have this chromatic dispersion. If we are in the anomalous dispersion case, so the blue that will travel faster. So we have the idea of kind of mixing these colors to understand that some balance can arise from that. Of course, there's a complete theory which was developed in the beginning of the 70s. And this works for what's called a Hamiltonian system, where you should have energy conservations, only dispersive effect. And we have a propagation equation, which is the nonlinear Schrödinger equation. So where the second term represents the chromatic dispersion, third term here is for the Kerr nonlinearity. And yeah, this is an equation for the envelope of the pulse, which means that the real electric field oscillates also with the carrier frequency, but we have the envelope of the pulse, okay? And well, of course, I will discuss more about temporal solitons, but as I said earlier, we also have a complete analogy with the spatial domain. So it's possible also to have spatial solitons. Let's give a bit more details about these solitons. Well, actually, they belong to a family, which means that once you, for instance, you have an optical fiber, the fiber has some properties with a chromatic dispersion beta 2, effective nonlinearity gamma, but this is not enough to determine the solution. The solution actually will depend on initial conditions. And so it depends on parameters due to its initial conditions. So for instance, the soliton duration. So you have some freedom, not only single solution. You can have either on the same fiber, either like a high energy short soliton, or you can have a long soliton with low energy with this soliton energy scaling here. It's an important formula. Okay, so since we have a propagation equation, it's rather easy to make numerical simulations. So we find, for instance, we can also verify the existence of the fundamental soliton, which means that even though there may be a lot of nonlinearity in dispersion, but you have this balance. And for this fundamental soliton, you have an exact balance. And that's the reason why no distortion, no change in the time domain, nor in the frequency domain. But there are also additional solutions, which are called higher order solitons, where at some time or some moment, some location in the propagation, maybe the nonlinearity will be exceeding the effect of chromatic dispersion, but that will be compensated a bit later on. So that on average, you have a balance between dispersion and nonlinearity, but expressed with these very nice oscillations in both the time and spectral domain. The first experiment proving the reality of these optical solitons in fiber was performed in 1980, and you have to figure out that at that time people didn't have this fancy diode laser operating in the telecom domain, so they use a very complicated source to access to the anomalous dispersion regime, which is required. And by changing the peak power, they could show that for a certain peak power, because their pulse duration was fixed, for a certain peak power, the pulse was almost the same at the output than it was at the input. So that's the case here of the fundamental soliton. And they also observed at higher power the higher order soliton, which was just illustrated here. I should mention the analogy with the spatial domain. So in the spatial domain, you can exchange the time dimension by one spatial dimension. That's easy. The difficulty is that actually we have two transverse dimensions. So with two transverse dimensions, the problem is a bit more complicated. But if you keep with one transverse dimension, you have exactly the equivalence. So you have situation where Kerr focusing can dominate or diffraction can dominate, and you can have a balance between Kerr self-focusing and diffraction. And that was observed in 1985 in an experiment using spatial nonlinear media, which is highly nonlinear, carbon disulfide. And they proved that this power-dependent propagation showing the spatial soliton. However, this doesn't work for two transverse dimensions. And that's the reason why for two transverse dimensions, you may have this collapse where intensity increases considerably and can give rise to a plasma formation. Continuing on analogies, I should also mention that actually soliton comes from hydrodynamics, with the first observation by John Scott Russell in, well, actually the observation was in 1834, and there were also actually in my place in Dijon, because we have a lot of canals. There were some early experiments some 150 years ago, but the math came a bit later, and some development to give the propagation equation in order to understand that's hydrodynamic soliton. But in nature, actually, if we observe the phenomenon of the tidal ball waves, it's also very close to soliton propagation. So in France, we have the well-known Mascaret on the Dordogne River. You can see like this river here is also channeling when you have this moon and asteroid effect, so it can channel some spatial wave here, and so that surfer can follow it for kilometers. But it's also well known in Brazil. It's called the Pororoca, I think is the name, and there are around 60 sites all over the globe. So let's try to see a real experiment with hydrodynamic solitons with a canal, which we have in our physics department, 80 meter long. And so that is for the observation of a soliton. So we release the wave. And because the height of the initial wave was well set, you have this soliton propagation. So it depends very much on that height here. It's also possible to show the nice properties of solitons owing to, for instance, their resilience to collisions. So this is another movie with this time two solitons with a head-on collision, which will be prepared. So suspense, shall it be destroyed? Not at all. The soliton is conserved even through collision. So after this presentation of solitons, I will go into the area of ultrafast lasers. So of course, the context is there's a lot of applications of ultrafast lasers, and in particular ultrafast fiber lasers. For instance, for industrial processing of materials like micro machining, etc. So why ultra short pulse should be important? Just because if you are with nanosecond pulse, nanosecond looks short, but it's not short enough, so that with nanosecond pulses, if you want to do micro machining, then there will be heat diffusion, and that will make some this kind of ugly craters. So not defining precisely the surface which you want to make. But if you have picosecond or even sub-picosecond pulse duration, it's athermal, non-thermal. You don't have the time, I mean, the thermal effect don't have the time to develop, and the energy will be creating a plasma, and this plasma will just take the material away without this heat diffusion. So it will make very neat contours of the structure. So those are examples of micro machining with high power ultrashort fiber laser. So it's possible to make like 3D complex elements like this metallic stand for heart surgery. But there are a lot of, let's say, a bit less fancy, but very important for commercial application, which is just marking. So by nowadays standards, many brands, they will kind of tag all their parts with this very small, very tiny print, which is maybe not visible in the naked eye. And this will be done in series with marking lasers, which are these ultra-fast fiber lasers as well. So why these fiber lasers are so interesting compared to bulk lasers? Well, just if you compare, bulk laser, yeah, can give some high power, but you have a lot of stuff that's costly. You have a lot of mirrors, you need adjustment, and also you cannot take most of your pump or your gain media because it's limited because of this Rayleigh range to just let's say a few centimeters. Whereas with those fibers, you can extract the pump energy. If you need 100 meters, let's take 100 meters. So that will make laser very efficient. Also, there are nice, so with this, those will be special fibers with dopants. They belong to the rare earth elements. And there are a few very successful elements like erbium, because erbium was used for first making the optical telecom amplifier. So it's around the 1.5 micron range. Then ytterbium around 1 micron, also very successful, and because it has a low quantum defect, so it's very efficient in terms of energy. So to make, for instance, if you can make kilowatt average power with ytterbium fiber lasers. And a bit more recently, there's a lot of interest with thulium-holmium dopants, just because they give access to the window, which is close to 2 micron, around 2 micron, also very broadband. So it's very interesting to have like an entry door to very close to the mid IR. And of course, the cavity, the fiber laser cavity, if you have a complete fiber laser cavity, is cheap because it's low weight. It doesn't need a lot of materials, and you don't need to readjust any mirror. So to make pulses, you need to implement some specific element, which is the saturable absorber. So the saturable absorber will be there to eat the noisy continuous wave and to just let the high peak power pulse go through. So that's a simple presentation. More precisely, it has a transfer function which ideally is like an S with a low transmission for low power, high transmission, high power. So if you have this into your laser cavity, then of course the laser is like a small intelligent animal which is looking the best way to laser and where there's the fewer losses. So that's the reason why the laser will self-organize to find a way, and this way would maybe with short or even ultra short pulses if you have a large gain bandwidth. And that's the way we can get passive mode locking, which means that the laser will generate ultra short pulses. So if you have one pulse, ultra short pulses going around the cavity, every time it passes close to the output coupler, you have an output pulse here. So it's like a clock, very regular. And that's the explanation, well, in the time domain. If you want to understand why we call that mode locking, you can get, so this is NAP from, I think, Wikipedia. Very nice, which shows you that like you have this coherent superposition of modes and which make the pulse. So that's called mode locking. So we need this saturable absorber. Either it's a material one, which means that we have special material like carbon nanotube, graphene, or CISM, which is a semiconductor structure, semiconductor saturable absorber mirror. Or we can also use the fiber itself in some special architecture where we will favor nonlinear interferences. So there are different possibilities to use nonlinear polarization evolution, or to have a structure with as a nonlinear loop mirror. So actually, for people who know, it's a derivation of the Sagnac interferometer with fibers and with some imbalance. So yeah. So that's the advantage of the fiber architecture. You can just plug and place or splice different components and do a lot of different architectures. In terms of commercial development, so in 1995 there was among the first fiber laser on the market. You can see its features already ultra short.
Bom, faço isso aqui, não tem senha. Para minha surpresa, agora também no computador.
Alexandre, seu microfone está aberto, Alexandre.
And so, okay, maybe I should speed up a little. We have this first commercial product. And 20 years later, there was like 3 orders of magnitude above in terms of in terms of average power or pulse energy, and that was because of the fiber laser architecture came as a master oscillator and power amplifier. So that's the current fiber laser technology with a lot of these applications in the industry. Okay, however, there are some issues with fiber laser because they use fibers, several meters of fibers. So there will be important nonlinear and dispersive effects. And that comes as a challenge because it will bring some pulse energy limitation and pulse deformation and breakup. It's also an opportunity because we have a platform to investigate ultrafast nonlinear dynamics and maybe to use those smart soliton effects. So why not to use optical solitons? So that's the solitons I described before. The difference is that now we think about solitons, but within a laser. So there might be more than just linear dispersion and nonlinear dispersion. The soliton laser was first presented in 1984, but at that time it was not a real fiber. It was not a real fiber laser. It was just 2 coupled cavities. Very complex modlock color center laser with just in a coupled cavity with an optical fiber to enhance the nonlinear Schrödinger soliton pulse shaping. And this was successful, and they worked with the n equal 2 higher the soliton. However, what's even more interesting in this paper is the vision. The authors say that, okay, maybe sometime just a special fiber could be enough. The soliton laser would most probably take the form of a single loop of fiber closed upon itself. The simplicity and low cost of such devices would make them most attractive. So it's very nice because it's a prediction which came true. Even at that time, they didn't have any fiber amplifier, fiber laser, but just a few years later, it came. So you see, less than 10 years after that, there were experiments with fiber lasers because the erbium doped fiber had been invented, especially for telecom, but also starting to be used to make fiber lasers. And people came across some at that time, rather strange features, which was multiple pulsing. They could easily get instead of one pulses going around the cavity, they could easily get 2, 3, 4, 5 tens of pulses. So it was a bit surprising. But of course, if you think in more precisely, just because we have this formula I've shown before, so and this is closely related to the soliton area theorem. Well, the energy is related to the fiber properties and the duration of the pulse. But if you pump more to your system, you cannot go beyond that energy, and then the response will be to make additional pulse to take care of the additional pumping and gain. Okay, so and people then come into a problem. So the pulse energy is not that much. It's around from 10 to 100 picojoule. It's not that much. They cannot compete, for instance, with Título lasers. So how to increase pulse energy? Play with the formula. Well, it's not that easy. The pulse duration is also limited by the gain bandwidth. It cannot be arbitrarily short. Well, it's possible to decrease the nonlinearity by increasing the effective mode area, but this relies on also a lot of fiber technology, and fibers become complicated and not compatible with other fibers. And also, don't think about increasing easily the anomalous dispersion. That's not, that's very, very tricky. And in addition, at that time, people did not understand why, well, okay, there's a reason why there's multiple pulses, but why all the pulses are so identical? If you think about the NLS, we have a family of solitons, so there should be something more. And this more is that we need to take into account at least 2 additional effects, which are not dispersive, but dissipative. You have to take into account the nonlinear gain and nonlinear loss. So this is a simple picture to show that this will define more precisely your soliton solution. So this becomes a dissipative soliton. Instead of belonging to a family, the dissipative soliton will be, for some parameters, it will be an attractor, which means you have a fixed soliton profile, and the attractor also gives robustness and stability. So at this point, I think it's better to give another analogy for people who are not in the field of ultrafast optics, so they can appreciate a little more. We take our sun. Of course, the physics of the sun is very complicated, but if you want to go to the lowest order of complication, you could take this model where the sun can be resulting from a balance between the internal pressure that tends to expand the sun, and gravitation, which tends to shrink its size. But also you have energy. In the core of the sun, you have nuclear reaction that generate energy, and radiation, which also removes this energy. And you have here the example of a dissipative solitons with two strongly coupled balances, which means that you cannot take balances separately. Because if you, for instance, if you kill something, you kill the internal pressure, or you kill gravitation, for instance. If you kill gravitation, the sun will blow up, but also the nuclear reaction will cool down. So strongly coupled. So that's the same with our pulses. This is just to express the fact that, of course, there are deep origins in this concept. So we already have the soliton theory with the idea of a balance between several physical effects. There were the ideas of self-organization in open systems from Turing to Prigogine. And also all the tools provided by the science of nonlinear dynamics with attractors and bifurcations. Yeah, if you want to play with this, with a model for dissipative solitons, you can play with the parameters of this cubic quintic Ginzburg-Landau equation. This is one example of a universal model for dissipative soliton. So it looks complicated, but each term has an explanation. So left-hand side is the nonlinear Schrödinger equation, and right-hand side you have the except to this correction to the Kerr effect, you have all the dissipative terms here, and they are very important. And their sign also is very important. So if you have linear loss, nonlinear gain, and saturation of the nonlinear gain, so with this sign, delta negative, epsilon positive, mu negative, so it will make like something sort of differential net gain, which is making this kind of curve, where you have the idea of getting to some special point, to some optimum here. So we have parameters to play with, and according to the parameters, for example, here we just play with the nonlinear gain epsilon, and then it's not like the NLS solitons, which had a such profile for the fundamental pulse. Here you can change the pulse shape from flat top to quasi-Gaussian or to such. So it's it's surprising. Not so much because you have many parameters, but what's surprising is that all these solutions can correspond to a very strong attractor. So another feature which is important is not just the profile, but also the phase profile, not just the intensity profile, but the phase profile. I remind you that the NLS soliton has a constant phase across its profile. And this means actually that there is no energy flow. And we remember from our electromagnetics course that energy flows through phase gradients. But now, dissipative solitons, they need some non-uniform phase because they need this internal energy flow to redistribute the energy to maintain the pulse shape from the regions where there will be net gain to the region where there will be, for instance, absorption. And this is an essential feature, is that dissipative solitons, they have both linear and nonlinear frequency chirping. So we see the evolution of models. So from the NLS solitons, and we have now the dissipative solitons with those couple balance. So how about just playing with these physical effects, like with the forces in a 2D plane? So For instance, we could try to compensate Kerr nonlinearity and normal dispersion with some special nonlinear gain and loss with these tilted forces. And so actually that is represented by gain, dispersion, and spectral filter. Namely, we want to make pulses in the normal dispersion regime because it's maybe convenient, 1 micron, invisible, etc. Whereas we could not have this original dispersive soliton here. And actually that was demonstrated theoretically, numerically. And also there was a very nice explanation from Hammond-House, even before the concept of dissipative solitons, with the idea that when you have a highly chirped pulse, just spectral filtering will also eat the taste of the pulse, just because of this very strong frequency chirping. So spectral filtering will actually shorten the pulse. That will be amplified in the gain section, and then due to sulfate modulation, subsequently the pulse can recover its original shape. So you can have either globally or in sequence a series of physical effects that allow something that people didn't think was really possible, which is to have ultra short pulses, even though they are chirped, in the net normal dispersion regime. And for fiber lasers, that had some consequences because that allowed to, because with chirp pulses, it's a bit close to the concept of chirp pulse amplification, actually, for which Strickland and Moore had the Nobel Prize a few years back. If you have lower peak power with chirp pulse, you can you will not break your gain medium, and you can extract more energy. And that's how, for instance, in this fiber laser, they could get more than 100 times more energy than with the NLS solitons. So this is maybe at the expense of the pulse shape and spectrum, because of course you output a pulse which is highly chirped, so you have to compress it afterwards, and also the spectrum develops those strange features. So there's a little price to pay, but otherwise you can have a lot of energy in the normal dispersion with fiber laser. Okay, so just a word about this attractor. So the notion of attractor means that it's also a noise eater. Noise eater means that, well, actually that's the reason why it's a special, when you have a mod-log pulse, of course it's going round and round your laser cavity, like people running in a racetrack, right? But if you look at the accumulated distance, excuse me, after maybe after a few hours, it's been traveling for billions of kilometers. So you don't have any equivalent. You don't have any equivalent with the dispersive soliton. So this is really unique, and this is because of this attractor. Okay, so I have maybe some 10 minutes to, if it's okay. I don't know.
Yeah, it's okay. It's okay.
Yeah, it's okay. You can
Fine.
take as much as you need.
Okay, so to go into this research zone where we have this weird dynamic. So I just explained about attractors, dissipative soliton attractors, but we can also have attractors not for a single pulse, but for what we call soliton molecules, because if you have several pulses, well, they are like in a prison. They are in the same cavity, so they always see each other, so they will always interact, and there are different outcomes of interaction. They kind of repulse each other, but they can also, for some parameters, they can also attract. And it's possible for some parameters that they lock and they form the equivalent of a molecule of light pulses. And there is a corresponding attractor. And when you have this molecule, it's very clear because it's very stable. Again, it can travel for the equivalent of billions of kilometers. And so how to observe that? If you have the chance to have a very fast sampling scope, you could see this molecule. Otherwise, there are other signatures, because if you have two phase lock pulses nearby, in the spectral domain, you will have spectral interference with this cosine modulation, where the and when the interfringe will in the frequency domain will be the inverse of the pulse separation in the time domain, and also you can use optical autocorrelation. So those are these soliton molecules, and indeed it can be so stable that even with a very refined cross correlation, balanced cross correlation measurement, you hardly get the timing jitter. So, for instance, there was this experiment where they proved that it could go below femtosecond timing jitter. But on the other hand, everything depends on the system parameters. So system parameters, for instance, the loss, time power, dispersion. So if you crank up one of these parameters, you can completely change the dynamics. So for instance, this is called bifurcation. So you can go from a stable focus attractor, this is one example, and you end up with a limit cycle attractor. So again, if we take analogy with astrophysics, we know we have our star, our sun. I present it like a dissipative soliton, but we also have pulsating star. Pulsating stars, they have this the dynamics which correspond to a limit cycle attractor. So let's get back to our optical solitons in lasers and soliton molecules. So let's take a molecule. We can have a stationary molecule, for instance, with sub-femtosecond timing jitter, and change parameters, system parameters, and we can discover that we set a motion, like a vibration between the two solitons that form this molecule. So initially we had we found that in 2006 with in direct measurements, and more than 10 years later we proved that with the special DFT measurements. So I will explain later. Those are just to give you a glimpse, because yeah, I will not take too much of your time, and also I don't want to lead you into confusion, because we have a big area of nonlinear dynamics where you can access to a lot of possible scenarios. So there's a lot, in general, a lot of complexity. So complexity can rise because we start from just a single pulse and we add more pulses and we let them interact, and we can form some special patterns like molecules, complexes, or even macromolecules and crystals of light pulse. But there's another direction to unfold the complexity, which is to go through these bifurcations, where you start from something stationary, even though it's with pulses, but stationary, and you can have this some kind of overall oscillation that evolve. And if you go through, for instance, other kinds of bifurcation, you can even have some chaotic dynamics. And of course, the fun is really to mix the two, so to have pulsating and chaotic dynamics with a lot of pulses. And of course, that's completely very far from the original mod-lock laser, which we use for like an on-off switch for a given application. All right, so yeah, needed to explain a bit the method actually to analyze the situation for each pulse for each output pulse, and the idea is to let the output pulse propagate through a dispersive low loss medium with a lot of dispersion, so that it will be equivalent to the far field diffraction regime. And actually, I already presented the fact that you have these two wave packets, like the blue and the red, separate. But you can generalize that for all. I mean, all the wave packets, all the frequency packets that make the pulse. And to understand that, after this high dispersion, the pulse, the stretch pulse, will take the form of its optical spectrum. And this is just Fourier far field diffraction regime here, but in the temporal domain. And so you just plug this output to your oscilloscope, and this is the first time you see that it's kind of magic, even though it's very logical, very simple to calculate. But for the first time, it's wow, you're impressed, because you have here, for instance, you have the spectrum of each output pulse, and you can have spectra at megahertz to gigahertz repetition rate. So it's really, I mean, there are a lot of applications for that. And for us who study ultrafast nonlinear dynamics, it's very valuable tool. So in the past few years, there's been a lot of research, for instance, to understand mod-locking dynamics using this tool, which is called DFT, for dispersive Fourier transform technique. And in our group, we also focused on soliton molecule dynamics, and that's the way we prove this vibrating soliton molecules just by recording successive spectra. For instance, here you have 2,000 successive spectra, and that showed us oscillation. Of course, we need to process the data. So we process the spectrogram, because the spectrogram has information about the pulse separation and relative phase. So we can do that by Fourier transform and can process this way the whole data. Just to show that we can operate with different platforms, different wavelength. Of course, when we work at 1.5 micron, we have the telecom fibers, which are very useful. So you can have like 6 kilometers of dispersive compensating fiber to have highly stretched pulse and get the optical spectra. If you work at 2 micron, you cannot propagate for 6 kilometers, not even 600 meters, just because absorption will be there. And then there's another trick, which is to use chirped fiber Bragg grating that will imprint a lot of chromatic dispersion, and this way, we're able also to work at 2 micron. So what we get are those recording here. So vertical, you have the number of round trips, and you see the evolution. Different types of evolution will show different types of kind of motions. So if you think about your 2 solitons locked in a molecule, and then they can, for instance, start vibrating, which is this kind of motion, and also they can also oscillate, which is a mix of separation and relative phase oscillations. And you can also have the sliding phase, which means that the phase will just spin around, the relative phase will just spin around like that. And this is very nice because you can distinguish. So to distinguish the different dynamics, so we perform actually a Fourier transform from this spectra, and this way, so actually that's the Wiener-Kirchhoff theorem. Yeah, we get the first order autocorrelation, and Actually, this also has information about because you can when you perform the FFT, you have also complex numbers that would give you access to both the relative distance between the two parts, but also with the relative phase, and you can reconstruct the trajectories of this phase and distance oscillations here. So that was an example where, for instance, a bit weird, it was not an oscillation, not harmonic oscillation, but very anharmonic. So okay, that was just yes, it's about time. So maybe just a couple of words about another topic, which is another weird topic, which is a incoherent dissipative soliton. So this is really weird. To understand that, you have to scratch your head, because this is in the situation of chaos. So and normally mod-log pulse means that you require some stability. Otherwise, you know that if you disrupt the mod-locking, usually you will end up into a just continuous wave or quasi-continuous regime. And there is some kind of intermediate situation, which is very weird, because at the same time you have a localization of pulse within a few picoseconds or a few tens of picoseconds, but within the pulse, a lot of chaotic wave evolution. So you have some instability, strong instability, but at the same time, localization remains. And that's been very, very puzzling. It was discovered by Horowitz and all in '97, and there will be a lot of investigations. Okay, I will speed up a little just to say that actually, so that's a modeling that we made showing that, well, actually, you don't need all these weird effects. I mean, high order effects, Raman, polarization, coupling, etc. Yeah, just a simple model with well-chosen parameters can also give rise to this effect. So this is in the normal dispersion regime. You see that you have mode locking, but this mode locking will give this chaotic pulse. In the anomalous dispersion regime, it's different because you have kind of soliton pulse shaping, but it will never be stationary. So this way, we understood that, yeah, it was possible to put forward another concept, because actually some people before on a different area, they placed forward the concept of incoherent soliton. So now we also want to explain these features with the new concept, which is that of incoherent dissipative solitons. And I think my time is over, and this is just a small figure to show you that, well, if you are interested in fundamental nonlinear dynamics with short pulse formations in lasers, actually what we use is just the tip of the iceberg. What we use is the stationary mod log pulse, and that's just the tip of the iceberg of nonlinear dynamics, because there's a lot of different dynamics which are non-stationary, even chaotic, where a lot of interaction among pulses. So, and yeah, so you can have a complete passage from coherent dissipative solitons to incoherent dissipative solitons. And I should stop there, and thank you for your attention.
Well, thank you very much for this very interesting talk. Let's say
open the microphone. Yeah.
I don't know what's happened here with. Okay. Okay, so I think that we can go for the questions
Questions.
section. Maybe there are several questions because that was a very interesting talk, and I know that some of my colleagues like very much this subject. So, someone has a question?
I'll go first.
Yeah.
Thanks for the nice talk, Dr. Grelu. So there's one particular kind of rare earth atom that would be better to study this or that nonlinear effect, or are they pretty much the same? Because I work with ytterbium. I think most of your work is done on erbium, and you also show thulium, something like that.
Yeah.
What do you think?
Yeah. So yeah. Very nice question, because initially, well, you've learned, of course, you know that my work is many more in the fundamental area. So not so for the moment, not so much in applications. So I like to show some general concepts and general features, and they say, okay, you can change the wavelength, and in principle it should work. Well, we also have the issue of chromatic dispersion. This is true, because if I work with erbium, I'm easily in the anomalous dispersion regime. With ytterbium, you are in the normal dispersion regime. But however, it's nice to see that there's many concepts can be changed, can be extrapolated to other laser architecture, other pulse energy, other wavelengths. However, so we mentioned chromatic dispersion, which may not be easily accessible. Well, you also have some strategy. You can have some dispersion compensation, even with bulk grating, etc. But for instance, moving into the infrared, you will remain with anomalous dispersion. But we started some experiments, for instance, with thulium, and we noticed that, yes, there are similar dynamics which we can observe, but there are also new features. Because different gain media, they will, for instance, have also different bandwidth. And when you work with thulium, you have a very, very large bandwidth. And what we observed, for instance, was it was possible to have simultaneous mod locking over different bands. So you can have different, actually different mod lock wavelengths altogether, which we didn't really observe in erbium. In erbium, it would be very difficult to do that. Some people do that, for instance, but they need to put some special filters. So yes, the gain median also, because of this, its bandwidth, also the wavelength region and chromatic dispersion, there is a role. But yeah, there are universal dynamics for sure.
Okay, thanks.
I think that there is another question by Anderson. He raised his hand. Okay, Anderson.
Yes, thank you. Yes, very enlightening talk, and bright and dark.
Yeah.
In the late 80s, Philippe, you certainly know a lot of work from Imperial College and older from Russia on what was called at the time soliton Raman ring cavities, control of soliton self-frequency shift with Raman, and so on. Noise-like pulse, like you showed. Of course, at the time, was more empirical, no deep theoretical work, mainly experimental work and empirical explanation. Every time I see a talk about this subject that you talked or see papers, can you reconcile all those old data with the more recent theory that you and a few others have put together?
Oh, this is very ambitious, but I also believe that some other big theorists yeah, they have taken care a bit of that. So I'm myself, I will not say, yeah.
Those all of those did not use rare earth doped fiber. Was
yeah.
silica. You know this.
Yeah. Well, it's yeah. For instance, yeah, if it's not completely easy because at that time people were not also recording the data in an appropriate way to have all the required features. I would say something like that. Yeah, well, it depends, but for instance, you take an experiment. What I think is what about the first important experiments in nonlinear fiber optics by Lin and co-workers in 1988, I think. No, 78. In 78, and they launched a very high power into the optical fiber with a complicated source. And it was at that time it was in the normal dispersion regime, and actually they got a forest of nonlinear effects where you could see some Raman scattering and also some continuum appearing, extending into the infrared. And so I know that some older scientists more experienced than I am took some time. So he was John Taylor from Imperial College. He also revisited this kind of experiment to show that from the old data, you could find actually the initial idea of supercontinuum generation, for instance, where you have some hidden soliton effects coming at some point, but data was insufficient really to completely prove the effect, or to basically redo, to perform the numerical simulation in a convincing way. So some people, some older experts than I am, they took care, they did some checks of the older experiments, and I'm not aware of everything in that respect, but for sure, because you could say, well, there are some easy experiments. Well, you got a lot of complexity, and you can record that, and maybe it requires another 20 years so that people can really get the theory. But but at the same time, you see with DFT, for instance, what we did, let's say we were the first to observe the vibrating soliton molecules, but initially we did not convince many people because we had the numerical simulation and we just recorded some average measurements. So it took some 10 years, more than 10 years, that we had the idea, let's do that with DFT, real time. And there was so we had a good paper, and at the same time also there was other authors, Eric, who also published in Science, and there was an explosion of actually old physics, but with new experimental methods and data, and
Okay, thanks.
Well, more questions?
Question. I have a question.
Yeah, go ahead, Lucio.
Okay. There are two questions, matter of fact. One is just out of curiosity. If you take a student and put him to work in this field, what do you say is the most critical parameter for him to take care of to achieve the different situations where you have, for example, a soliton molecule? Which parameter, laser parameter, you say is the most critical? And that's one question. And the second question is regarding the soliton molecules. I would like to ask you to tell us something about typical distances, temporal distances between the pulses, and how can you have them? How far can you have them, for example? Okay. So
yeah. So yeah, about the first question is, I mean, if you have the idea to train a young experimentalist, and well, this takes a bit of time. For instance, you have to train it about him or her about fibers, handling the fibers properly. Then about assembling a cavity, checking the components, and then using the expensive equipment. So, for instance, I pay attention so that he will not plug anything on my very fast, expensive scope. Because if you, for instance, you plug 20 volts, then it goes for repair, and you pay maybe 5,000 to 8,000 euros. So yeah, there are some all these steps.
The question,
but yeah, I know. Your question is what parameter? The parameters. Well, for instance, if I take a student, I want him to have easily this soliton molecule. So let's work with erbium doped fiber in the anomalous dispersion regime, because in that regime we'll have a lower, because there will be anyway some soliton shaping effect even from NLS, which means that you won't have as much as a chirping, and energy will be also limited, so that you just crank up the power, the pumping power, and you will have more pulses. And this is the easy situation. I mean, as I told, like in the 91, 92 experiments in Southampton, for instance, they were surprised because it's very easy, even with 50 milliwatts of pumping power, which is very low with pumping diode. You can have several pulses, and then, of course, you need additional parameters, and these additional parameters, they depend on your saturable absorber. So for that reason, I like to use a completely versatile saturable absorber, which is, for instance, with nonlinear polarization evolution, which means you have knobs on the nonlinear transfer function, and that's in practice, that's very, very important. Your second question was about the typical distances. These distances. So if you want to have a robust soliton molecule, so it should be just a few pulse width apart, because basically interacting through their tails and locked in phase, and you will have stable, robust soliton molecules. But it is also possible to have distant soliton molecules, where you can also link them with some intermediate, which is like some quasi-coherent radiative wave, for instance, which is linked to the Gordon-Kelly Sibons, or other ways also is possible. So you can have like some intermediate action to link pulses far apart, but if they are too far, of course, it will be a weaker bond. So the binding will be weaker, and it's easily distorted. Yeah.
Okay. Thank you very much.
Yeah, welcome. Yeah.
Siri, você está sem som. Está sem som.
Oh, yes. More questions? I have one question. You have this analogy between time and space. Is there any proposal, is that a possibility to observe a soliton molecule in the spatial regime? Did anyone did experiments with that?
So actually, in this, yes, in the spatial domain, there are experiments with VCSEL lasers. So VCSELs, vertical cavity surface emitting lasers with large area, and they can, they have the equivalent of dissipative solitons in the spatial domain, and they have these dots, lasing dots, and which can interact and form the equivalent. So there are groups, of course, who work in the for 10, 15 years. Well, actually, even I think it started. There was a paper by Barlan and co-workers. I think it dates back to the early 2000s, something, 2000 something. Maybe close to 20 years ago. Yeah.
Who was the person? You mentioned the name.
I think it was Barlan, maybe with Tredice and with maybe Tredice and Lugiato.
Okay.
Yeah.
Okay, more questions? If there is no more question, I would like to thank you again for this very interesting talk. Hope that we meet sometime again in France or in Brazil.
Yes, you are welcome. If when you can travel, if anyone passes by, welcome in the lab.
Yeah. Okay. So if there is no more questions, so let's thank the speaker again.
Thank you very much. I also appreciated these nice interactions and your questions, and it's very
Thank you.
I like it. It's like we are. I mean, not do these many 1,000 kilometers apart. So that worked well.
Very good.
Okay. So
Well,
I think
let me ask you here again about the soliton separation in the molecules. If you have, for example, a normal dispersion laser like ytterbium and so on, the pulses broaden and shrink very strongly because of, well, if you use diffraction gratings, for example, to compensate dispersion. Does that allow you to have further separated molecules? Because it, as you know, or if the power is too low when it stretches, the interaction is linear and therefore not relevant. Understand what I mean?
Yes, sure. So I don't think it allows you to because this soliton molecules also needs. So it's more difficult to have soliton molecules when you have a lot of chirping, just because there will be some phase-related problem where the tails of the pulses will meet. However, it is possible, but in from my experience and from the little I know from little literature also, it requires a stronger overlap of the tails, which means that the pulses will not be so separated, but they will be actually most of the time strongly overlapped. Okay. To the point that you may miss the fact that there are two pulses.
Okay.
You can see only maybe one big hump. In the autocorrelation, it's only when you compress that structure that you say, there was two. There were two.
Okay. Okay. Thank you very much.
Okay.
Thanks for your question.
Okay, more questions? No? I think that now we finished. Okay, and I thank you again for the interesting talk.
Thank you.
Goodbye.
Bye.
Goodbye.
Bye.
Thank you all. Goodbye.
Goodbye.